Hello student, please join. So anybody there? Please tell me. Good morning everybody. Good morning everybody. Am I audible? Please tell me. Good morning Shubhodip. Good morning Sharupa. Good morning Sharnamo. Shashwati, good morning. Shohini, good morning. Arunima, good morning. Shubhoshree, good morning. Sharupo, good morning. Okay. So Anirvan, Anirvan, are you watching? Okay. So today I am discussing some constructional method of generalized inverse. First I define diagonal. Yes, Shubhodip Gain, good morning. Oh yes, Anirvan. Okay. How are you? Anirvan, how are you? So diagonal reduction let capital A be a matrix of order m cross n and rank of A equal to small r, which is less than equal to minimum of m comma n, then there exists non-singular matrices B and C of order m cross m and C of order n cross n such that BAC IR is identity matrix of order R 0 0 0. So this is always possible using non-singular pre-multiply and post-multiply by some elementary matrices. So for I illustrate this through an example. Suppose I consider matrix A whose order 2 cross 3 and the elements are and if we multiply identity matrix order 2A and identity matrix of order 3, then this gives matrix A. So that is so. Now I use row operation first. So R1 star, this gives the new row we obtain by R1 by 3 row operation means pre-multiplication. So I apply this operation on this matrix 101. So 1 by 3 0 0 1 3 1 0 2 0 1 1 0 0 0 1 0 0 0 1. So this gives 1 1 by 3 0 2 0 1. Next R2 dash this is equivalently R2 minus 2R1. So this is equal to one by 3. This is a row operation, so I apply this on my first matrix 1 3 0 0 1. So this is minus 2 by 3 1. So actually this is obtained by just 1 by 3. This is a first row multiplied by 2 and this is a second row minus, so this gives 0 minus 2 by 3 1 minus 0. So this is minus 2 by 3 0. So this is the second row. After these elementary operations you get the second row is minus 2 3 1. Okay, so this is the procedure. is equal to, similarly 2 0 1, this is the second row of this matrix, minus 2 into 1 1/3 first row, so this gives 1 1 3 0. So second row is now changed and it is 0 minus 2 by 3 1. So this is 0 minus 2 by 3 1. Now I use column operation. C2 dash I can use arrow or curl. C2 dash C2 minus 2 by 3 C3. So then column operation means post multiplication. So this operation I apply on this matrix. Okay, 1/3, this is unchanged. One zero zero. Now C2 0 1 0 minus 2 by 3 0 1, then that means 0 1 minus 2 by 3, so 0 0 1 equal to, sorry, this should be a column operation. So 0 0 1 minus 2 by 3, this should be a minus 2 by 3. Okay, actually it is better you use this operation. That is, our aim is to reduce this matrix to IR00 form. So for this I use simultaneously row and column operation. So it is better to use this operation. C2 curl 1/3 C1 minus C2. So this is 1/3 1 0 1/3 minus 1 0, sorry, because 1/3 C1 minus C2, so this is 1/3 minus 1 0. Check it, just 1/3 1 0 0 minus 1 0 0 1 0. That is 1/3 minus 1 0. Okay, so now again this is the first row, first column of right hand matrix, minus 1/3 minus 2 3. So this is 0 0 plus 2/3. So this should be 1 0 0 2/3 0 1. Okay, so next C3 dash, this is equal to, actually I make this one or replace this one by 0, so we need this operation C3 dash curl C2 minus 2 by 3 C3. So 1/3 0 minus 2/3. Yes, Anirban, good morning. Two zero one. So 1 0 0 1/3 minus 1 0 1/3 minus 1 this is minus 2/3. So then you get 1 0 0 2/3 0 0. So now convert this 2 by 3 to 1, then you use row operation R2 dash equal 2 3 by 2 into R2. So this means 1/3 0 minus 1 3 by 2 3 2 1 0 0 1 1 0 0 1/3 minus 1 0 1/3 minus 1 minus 2/3 equal to 1 0 0 0 1 0. Okay, so please tell me whether the calculations is correct or not. If correct, then I proceed further. Please check. Subrojit, I do not understand what you want to say. You just write same operation. What same operation means? Subrojit, are you hear me? So please tell me whether the calculation is correct or not. If not, please tell me the mistake. Otherwise, I continue. No doubt, no doubt. Okay, thank you, Sharpa. Thank you, thank you. So this matrix is B here. This is A. This is C. You can easily say that B and C both are non-singular matrix because elementary operation means pre-multiply or post-multiply by non-singular matrices. So these are nothing but a product of some elementary matrices, this portion, and this is also the product of sub-elementary matrices. So this is a full range matrix and these are B and C are non-singular. Clear? So here B is and C is okay. Now I denote this by number 1. Now from 1 since B and C both are non-singular matrix, so I write A as B inverse IR 0 0 0 C inverse, and this is equal to B inverse IR 0 0 0 IR 0 0 0 C inverse. So this is nothing but a capital P, and the order of P is now M cross R and Q is R cross N. So now I convert. Now first we find the inverse of a matrix B. So B inverse is equal to, you can check this, determinant of B is simply half. So B inverse is three, then this is 2 by 3 minus 2 0. Am I right? Please tell me. Sorry, this should be a 2, I think. 2. Please tell me, is there any Anything wrong? Please tell me, otherwise I continue. Will you get same values or not? B inverse, then C inverse equal to 1 0 0 minus 1/3 minus 1 0 0 3/2 minus 3/2. So please tell me, please check B inverse and C inverse. If these two things are correct, then I continue. You can check in that way also, C inverse, whether C inverse is I or not. So first thing is 1, first element, then second is 1/3 Z. I think this is wrong. So tell me, then this is 0, 1/3, there should be a, so please find C inverse and tell me the first row. Find C inverse and tell me the first row. You do it fast. So what is the adjacent of, I think it is 2/3 most probably. 2/3, what is the determinant of C? This is a upper triangular matrix, so determinant of C is 1 minus 1 minus 2/3, that is 2/3. So first element is 2/3, then this is 1, this one is correct, and then 1/3 0 minus 1, that is plus 1. So this is a 2/3, I think this is a 2/3. Minus 2/3, I think this is a minus 2/3. So tell me first, this is a minus 2/3. Okay, so 1/3 minus 2/3, that is 1. Now this thing is, then 1/3 minus plus 2/3, 0. So I think first row is correct. Now the second row. So for the second row, this is 0 minus 2/3, 0, 2/3, 1. So this is the transpose. I think this is the 1. So done. Yes. So tell me the first row, Subhrojit. I think first row is correct. Now the second row. What about the second row? Subhrojit, are you hearing me? Please tell me the second row. First row is 3 0. Uh, Second row is 2 to third. Okay, this is a B inverse. Okay, 3 0. First row is 3 0. Second row is 2 to third. And what about the, okay, B inverse? What about the C inverse? What about the C inverse? I think wrong, Suprajit. You need to take transpose of this matrix. If you take a BB inverse, then it should be 1/3 0 minus 1 3 by 2. I think you are wrong. I think you take a transpose of this matrix. So this is 1/3 1 0. See, 1/3 into 3 0, then 0, then 0 0. Okay, then minus 3 3 0. Okay, you are right. 0 1. Okay, correct. This is correct. What about C inverse? Subrojit, what about C inverse? Tell me. First row, second row, and third row. Tell me. Subrojit, Subodhir, anybody tell me the second row of C inverse? Sohini, are you there? Okay. Subrojit says first row is 0 minus 1, 0 minus 1, 0, Subhajit, is it a first row? Zero minus 1, 3 by 2. Subhajit, is it a first row or not? Is it a first row, Subhajit? Are you hearing me? Please. What about the other people? Only Subhajit answered the question. Oh, this is the second row. Second row. This is second row. Okay. What about the first row? This is the second row. What about the first row? Okay, first row is 1, 1/3, 0. First row is 1, 1/3, 0. What about the third row? Sohini, Swarupa, Swarupo, Dhishari, please answer. Only Suprajit answering the question. Okay, third row is 0, 0 minus 3 by 2. Thank you, Suprajit. So, you can check whether your calculation is correct and wrong. Just see C inverse, whether C inverse I or not. If I, then your calculation is correct, otherwise you need to check. Okay, thank you, Shoini. So now we get B inverse C inverse, then multiply C. B inverse by this then we get okay. So so this is just C inverse, that is 1 1/3 0 0 minus 1 3/2 0 0 minus 3/2. So hence this is our P. We can easily check that this is a full rank matrix, full row rank matrix, full row rank matrix, and this is our Q. I think I did some mistake. So this is our B, okay, and this is C, and see that if you take this is P matrix, P, then what happened really, this is 2 cross 3 and this is Q 3 cross 3. This is a full full row rank matrix, and this is full column rank matrix. So since this is a full row rank matrix, then right inverse of P exists, and it is P prime P prime whole inverse. And since Q is a full column rank matrix, then left inverse exists, and this is equal to Q prime Q whole inverse Q. Okay, so sorry, Q prime. Now G inverse of A, that is G whose order 3 cos 2, then this should be QL inverse PR inverse. Please do it yourself. Okay, then using this matrix you can find also Moore Penrose inverse, that is equal to Q dash here it is Q means order 2 plus 3 Q dash Q prime G inverse or inverse P prime P inverse P prime. So please complete this thing. So this is the process to find G inverse and Moore Penrose inverse. I will discuss another method after completing eigenvalue eigenvector. So the steps are: first you start with the steps are, can I rub this portion? Yes or not? I think I just rub this portion only. So steps 1, you start with I n a I n, if order of a is m cross n. This is a, so after row operation and column operation simultaneously, you get a matrix BAC. This gives IR000. So from this you find rank factorization PK, PQ. After getting P and Q, so you can easily find this G inverse and Moore-Penrose inverse. Oh, Swarnava, you are right. You are right. You are right. I okay. I again write this portion. Thank you, Swarnava. So okay, okay. Okay. So you know the G, after getting P and Q, you know the formula of G inverse. So G inverse is G inverse of a matrix A equal to, since here I see that left if P is a full column rank matrix, so this should be QR inverse PL inverse. So G inverse is QR inverse PL inverse. So you know the method how to find PR right in. Suppose you find the right inverse of Q, then use this formula. Q prime, then it is order R cross R, so inverse exists, and then this is pre-multiply Q prime. Okay, so this is the right inverse. Next, for left inverse you use this formula. I already discussed all this formula. Okay, IL. Okay, OQL. Oh, in this case Q, I think I tell generally. Okay, so okay, thank you. So you say UL inverse. Okay, in this case QL inverse exists, because I think QL is a full row rank. No. QL, I think QL is a, oh sorry, QL is a full column rank. So QL inverse exists. Then in that case it should be q prime q whole inverse q prime and pr inverse equal to p prime inverse p prime. Okay, so use this formula, you can find ql inverse pr inverse using this, so you can easily find g inverse of a, and you know the formula of Moore-Penrose inverse using rank factorization, that is q prime q prime whole inverse p prime p whole inverse p prime. So please do this calculation yourself and submit it and take it as your homework. Okay, so if you have any doubt about the calculation, please tell me. If you have any doubt about the calculation, please tell me. So here I want to mention this particular example. In particular example, here IR should be 0, IR 0. Okay, and C inverse, and here IR 0. Please check this thing. This should be IR breaking into two parts. Okay, listen carefully. And if you multiply this IR 0, IR 0, this gives IR 0, 0. So I replace IR 0, 0 by IR 0, IR 0. Okay, then your for this example, then your P equal to B inverse IR 0. So order of a B is 2 cross 2. So IR is a R is a 2. So P inverse 1 0 0 0 1 0, and Q equal to 1 0 0 1 0 0. But Q is a 3 cross 3 matrix, so we need this. Okay, so we need this. And this is C inverse. So this is the procedure. So if you have any doubt, please tell me. So for this particular example, we break this IR 0, 0 into these two parts. So depending on the order of a matrix B inverse and C inverse, we partition, we write this matrix as a product of two matrices, and order of these two matrices depend on the order of B inverse and C inverse. Okay, so please, when you break this matrix or you write this matrix as a product of matrix, you should be careful about the order of B inverse and C inverse. So please tell me if you have a more doubt, then I again illustrate this. Otherwise, I continue to the next part. So this is one of the constructional method of G inverse and Moore-Penrose inverse. Theoretical portion I already discussed in my previous class. So this is the example how to construct G inverse and Moore-Penrose inverse. Later, after completing eigenvalue eigenvectors, I will discuss another method of constructing Moore-Penrose inverse. So before discussing this method, I need to discuss eigenvalue eigenvector. So please tell me if you have any doubt regarding this example. So I will discuss, otherwise I continue to the next portion. Swarupas are clear. What about the opinion of others? Please tell me. No doubt, Shashwati, thank you. So can I wrap this portion? I think so. Shashwati, Swarupa, except Shashwati, Swarupa, please tell me the opinion of other. Shubhadeep say no doubt. Okay, thank you, Shubhadeep. Okay. Next, eigenvalue and eigenvector. I think Suraj say how to construct G inverse. Suraj, this is your answer. You asked me previous in my previous class how to construct G inverse. So this is the one of the method to construct G inverse and Moore-Penrose inverse. Happy? Eigenvalue and eigenvector. Thank you, Shubhashree. Let capital A be a square matrix of order R of order n. Of order n, then there exists x curl which is a non-zero vector such that a x curl equal to lambda x curl, where lambda is real or complex number, then x curl is called eigenvector of a matrix A corresponding to eigenvalue lambda. Now Ax curl equal to lambda x curl. This means A lambda in equal to x curl is a system of homogeneous equation. The system of homogeneous equation. So A minus lambda n is a singular matrix because x is a non-zero vector, and therefore this system of homogeneous equation has non-zero solution. This is possible when rank of A minus lambda in less than n. Hence A minus lambda n is a singular matrix. That means det of A minus lambda n equal to 0. So this is called characteristics equation and A minus lambda n, this is equal to lambda n plus n minus 1, lambda n minus 1, n minus 2, lambda n minus 2, a1. So this is a monic polynomial because the coefficient of lambda n is a 1, and this is called characteristic equation. Sorry, a characteristic polynomial. This is called characteristic polynomial of degree n, and we denote this by chi a within bracket lambda. This is monic polynomial. This is monic polynomial. Since coefficient of lambda to the power n equal to 1. Now for given lambda, for particular lambda, so this equation satisfy for such x, and the collection of such x such x vector is a vector space because it is a null space, and it is called eigenspace of lambda. So this is called eigenspace of lambda. And suppose we have lambda 1, lambda 2 t eigenvalues. For each lambda i's, we get a eigenspace lambda. I denote this eigenspace by E lambda. Then we get for each lambda I, we get lambda 1, E lambda 2, E lambda t. Dimension of, since it is a vector space, it has a dimension. So for a particular lambda, the eigenspace E lambda, dimension of eigenspace of E lambda, say it is k, then this k is called geometric multiplicity of lambda. This is called geometric multiplicity of lambda. And a minus lambda n equal to 0 if lambda is a repeated root because lambda is a root of this equation, and suppose it is a repeated root with multiplicity r, with multiplicity r, then this r is called algebraic multiplicity of lambda. So this R is called algebraic multiplicity of lambda. Now consider some example. Suppose a matrix A equal to 1 2 0 0 0 1 3 0 0 0 1 4 0 0 0 1 upper triangular matrix. Now A minus lambda I equal to 0, this implies, since it is the upper triangular matrix, then this should be a product of A minus lambda, again a upper triangular matrix whose diagonal elements is 1 minus lambda I, 1 minus lambda I, and we know that determinant of a upper triangular matrix is nothing but a product of a diagonal element. So it should be 1 minus lambda whole to the power 4 0. So here lambda equal to 1 and this one is repeated 4 times. So with multiplicity 4, hence 4 is algebraic multiplicity. Of 1, eigenvalue 1. Now A minus lambda I, here lambda now is 1, so this is simply A minus I and it is this. And we easily see that the rank of A minus lambda I is 3 because 3 rows are independent and this is easily checked. And we know rank of A minus lambda I plus null space of A minus lambda I, dimension of null space of D, dimension of null space of this portion, dimension of null space of A minus lambda I, and this is order of a matrix A, that is 4. And A minus lambda is 3. The dimension of null space of A minus lambda I, which is nothing but a eigenspace of lambda, and lambda here is 1. So dimension of E1 4 minus 3, this is 1. So geometric multiplicity of 1 equal to 1. So from this example we see that algebraic multiplicity of 1 is greater than geometric multiplicity. Now if we consider another array, then A minus lambda is again this 1 minus lambda whole to the power 4, and lambda equal to 1 with multiplicity 4, hence 4 is the geometric multiplicity of 1. Now a minus lambda a minus I, which is simply this. So a minus rank this equal to 0. Dimension of this equal to, so dimension of E1 equal to simply 4. Here geometric multiplicity of 1 is 4. So for this example we see that algebraic multiplicity equal to geometric multiplicity. Hence we claim that algebraic multiplicity of a eigenvalue always greater than equal to geometric multiplicity of a eigenvalue. Before proving this claim, we need the lemma Subhrojit, geometric multiplicity is 1 means geometric multiplicity for second example it is a 4. See that a minus I is a 0 null matrix. Rank of null matrix is 0. So dimension of null space should be 4. So dimension of a null space of a minus lambda is nothing but a geometric multiplicity. So for second example, algebraic multiplicity equal to geometric multiplicity, and for first example it is 1. So please tell me your queries clearly. Please tell me, I am waiting for you. Subhrojit, are you hear me? Please check your calculation fast. Then tell me. And okay, thank you. So before prove this claim, I need this lemma. So, oh, first example. Oh, actually I finished this first example and after finishing first example, in first example I see that geometric multiplicity greater than algebraic multiplicity greater than geometric multiplicity. And second example, I find that algebraic multiplicity equal to geometric multiplicity. So for this reason, I claim that algebraic multiplicity should be at least geometric multiplicity of a eigenvalue. Okay, so this is the claim. I need to prove this claim. So proving this claim, we need the lemma. We need this lemma. Oh yes, yes, yes. Okay, thank you. Lemma A and P inverse AP are similar matrices. Where P is non-singular matrix, two matrices similar. If A and B is two matrices similar, then if we represent B equal to P inverse AP, where P is a non-singular matrix. Okay, this is the definition of similar matrix. So I repeat this again, A and B, two matrices are similar if there exists a non-singular matrix P such that B equal to P inverse AP. This is the definition of similar matrix. So A and P inverse AP are similar matrices where P is a non-singular matrix. Then characteristic polynomial chi A, I already defined chi A by characteristic polynomial of a matrix A, lambda equal to chi P inverse AP lambda. So proof is simple. Chi P inverse AP lambda, this is equal to P inverse AP minus lambda I. So P inverse A lambda P so lambda P inverse so data of A B equal to data of A, data of B. These are scalar. Determinant is a scalar, so we can write this as also. Okay, sorry, Sharupa. Actually, I forgot this thing. So A minus lambda I. So this is equal to chi A lambda. Hence, we see that characteristic polynomial both the matrices are same. Hence, the eigenvalues of these two matrices are same. So, if two matrices are similar, this means the eigenvalues of these two matrices are same. Left hand side mean to say, Swarupa, what is your question? Oh, left hand side I mean to say. Okay. Now it is fine now. Is it fine? Or anything problem? Tell me, Swarupa. Can you see? So now I prove this claim. Thank you. Now I prove this claim. For given lambda, let dimension of eigenspace, that is the null space of A minus lambda I, equal to Kc. Let, since null space of A minus lambda I is a vector space, so it has a basis. So this is a basis of null space of A minus lambda I. Okay. And since null space of A minus lambda I is a subspace of Rn, because A is a square matrix of order n, I assume that. So we can always add some vectors x1 xk plus 1, xk plus 2, xn, such that x1 curl to xn curl is a basis of vector space Rn. I denote, or either it is better to say I construct a matrix P of order n cross n whose columns are x1 curl, x2 curl, xn curl. Since this is the basis of Rn, hence P is non-singular matrix. Okay, Shohini. Now, since it is non-singular, inverse of P exists. So I write In equal to P inverse P. And I denote the rows of P inverse by xi1 curl prime, xi2 curl prime, xi n curl prime. So this implies xi curl prime xi curl. This is the diagonal matrix of P inverse P, and P inverse P diagonal elements of P inverse P is 1. So this should be 1 for all I from 1 to n, and xi prime xi j curl 0 for all I not equal to j. Okay. Now characteristic polynomial of A for eigenvalue mu equal to mu I A minus A minus mu I. And we know P inverse AP is a similar matrix of A, hence characteristic polynomial of P inverse AP is same as characteristic polynomial of A. Now, P inverse AP, this is equal to we know basis of a null space of, mind it, please listen carefully. I go very slowly this portion. I will go this portion very slowly. Since null space of A minus lambda I has a basis, and I denote this basis by x1, x2, xk. Okay, That means a minus xi equal to lambda xi for what I? When I equal to 1 to k. Agree? Okay. So then is equal to x, it should be lambda x1 curl, lambda x2 curl, lambda xk curl, a xk plus 1 curl, a xk curl. So this is equal to again P inverse is xi1, xi2, xk. So it's equal to lambda ir ik see that xi1 prime lambda xi x1 curl, that is lambda xi1 prime x1 1 lambda. Similarly up to that xi1 gives lambda 0 0 0 first row, secondly lambda 0 0 lambda 0 0 0 so on up to k. Okay, so I write lambda ik simply using this portion. Now the remaining portion is a xi1 prime a xk plus 1, xi1 prime a xk, and so on, and I denote this by matrix C of order k cross n minus k. And since xi xi prime xi 0, so for xi k plus 1 xi n this portion should be 0, and I denote the remaining portion by t of the order n minus k cross n minus k. So are you agree? And denote, and where C is, where C equal to xi1 prime a xk plus 1, xi1 prime a xn curl, xi k prime a xk plus 1 curl, xi k prime a xn curl. This is C, and D is xi k plus 1 curl prime a xk plus 1, xi k plus 1 a xn curl, xi k plus 1 prime a xk plus 1, xi k plus 1 prime a xn curl. So I write these two matrices as follow. Now chi A mu. So this is equal to, I replace this matrix by this matrix, then this is lambda minus mu ik minus c 0 b minus mu I n minus k. This is equal to lambda minus k, lambda minus mu whole to the power k det of d minus mu I n minus k. This imply lambda is repeated characteristic root of A with multiplicity at least k, because chi A mu equal to 0 imply you get exactly, you get mu equal to k at least k time, and for these portions you may get a solution of mu, lambda as a solution of mu from this portion you may get. So that's why I write lambda is a repeated characteristic root of A with multiplicity at least k. And since we assume this is a basis of null space of A minus lambda, and assume these things, dimension of null space of lambda equal to k, so k is a geometric multiplicity, and from this derivation we see that algebraic multiplicity is at least k. Hence we get this result, algebraic multiplicity of A oh yes Disha, this is error. Okay, this is my mistake, sorry, thank you. So it should be n. Okay, thank you Disha. Now is it okay? Okay, so hence algebraic multiplicity yes Dishari, are you, is it right now? Tell me. Thank you for your comment. You are right. The last row should be xi n instead of xi k plus 1. Algebraic multiplicity of lambda should be greater than equal to geometric multiplicity of lambda. So this is the proof. So please tell me if you have any doubt. please tell me if you have any doubt. Can I rub this portion? Tell me, please quickly. Please tell me quickly. Lambda equal to k. Shubhadeep. Shubhadeep, this is the characteristic equation. So from this equation, you get mu equal to lambda at least k time, exactly k time for this equation, but you may get solution of mu as a lambda from this portion also, maybe get. So that's why I write at least instead of exactly. From this portion you clearly seen that lambda is a repeated characteristic root with multiplicity exactly k from this portion, and you may get solution of mu as a lambda from this portion also. For this reason I write instead of exactly I write at least. Clear? Shubhadeep Kain, tell me. Shubhadeep Kain, are you hearing me? Tell me, is it clear or not? Can I repeat once more? No problem. I have a no problem. Okay, thank you. Next theorem. A and B is a square matrix of order n cross n, and B is another square matrix of order n cross n. B2 square matrix then characteristics roots of AB and BA are same. Proof. Case 1. At least one of A and B is non-singular. Let A be a non-singular let A be a non-singular and Since AB is non-singular, then A inverse exists, and AB A inverse. This is a this is a similar matrix I already defined. If there exists a P inverse, there exists a non-singular matrix P, then A or B both are similar matrix if B equal to P inverse A P. So this is a similar matrix. So this is nothing but a BA. So if A is a non-singular, then AB and BA are similar matrices. Hence, characteristic roots of AB and BA are same. Next, case 2. That is A and B both are singular matrix. Both are singular matrices. Let rank of A equal to R. Then there exists P of order n cross R and Q R cross n, where P is a full column rank matrix. Q is full row rank matrix such that A equal to PQ or it is better to write in that way since I already discussed this thing. Then there exist two non-singular matrices P and Q. You take two non-singular matrices. There exist two non-singular matrices P whose order n cross n and Q whose order n cross n such that PAQ equal to IR 0, 0, 0. Okay. Now assume Q inverse BP inverse. This gives a matrix. I denote this matrix as partition form CD E F, where order of C is R cross R, D is R cross n minus R, E is n minus R cross R, and F is n minus R cross n minus R. Now AB Since P is a non-singular matrix, since AB and P inverse AB P are similar matrices, since P, I assume that P and Q both non-singular, so AB and P inverse ABP are similar matrices. Therefore, characteristic equation of AB and characteristic polynomial of AB and P inverse AB both are same. So this means sorry, I write this thing as AB minus lambda I PAB P minus lambda I. Okay, so this is equal to P inverse AB P equal to one more thing I want to tell you. So since P is a non-singular matrix, P inverse also a non-singular matrix. So these are same thing, because for this proof I need this portion. Sorry, so P AB P inverse. This is also a similar matrix. You can prove same way. Okay. So for this reason, the characteristic polynomial, both the cases are same. These are same thing. You can easily check this thing. So characteristic polynomial of AB and PAB P inverse are same. So I need this thing because of my proof. Instead of P inverse ABP, so it's equal to P A Q inverse BP inverse. So this gives I. Q inverse equal to I. So instead of I write Q inverse. So this equal to this matrix, and PAQ I take I at 0 0 0. So this equal to so this is equal to CD00. So now PAB P inverse minus lambda I, so this is nothing but a C minus lambda IR D0 minus lambda I n minus R. Okay. and this is equal to minus lambda whole to the power n minus r date of c minus lambda ir. I denote this by equation 1. Again, Q inverse B P inverse P A Q, this is equal to Q inverse B A Q and B A are similar matrices. Hence, and this is equal to CDEF into IR000. We get this matrix after multiplying this CE00 and then chi AB chi BA lambda equal to chi Q inverse BA Q lambda equal to C minus lambda I 0 E minus lambda I n minus r. So this is equal to minus lambda whole to the power n minus r date of c minus lambda. Hence we see that characteristic polynomial of characteristic polynomial of BA and characteristic polynomial of AB are same. So please tell me if you have any doubt. Please tell me if you have any doubt. Okay, thank you, Shobhit. Thank you, Sharupa. Thank you, Shohini. Suppose this is a remark. Instead of taking square matrix, Swarnabol, after remark I will finish. Please give me a time for just telling the remark portion. Okay. So suppose I have two matrices A of order n cross m and B is order m cross n, then using same process you can prove that. Thank you, Sharnabo. This. So this is your homework. Please solve this portion using same procedure of the theorem. Just I prove this proof. You can easily prove this one. So please do it yourself. So I want to stop today. Again, we will come back on Thursday. On Thursday, yes, Thursday, next Thursday. Till then, thank you everybody. And hope you will enjoy this class. And in next class, I will discuss characteristic root again, and then if I get time, then I start the next constructional method of Moore-Penrose inverse. Till then, thank you. So if you have any doubt, please tell me. Otherwise, I want to close the stream. Thank you, Shohini. Thank you, Sharupa. Thank you, Suprajit. Shashwati, thank you. Thank you, Shubhodip. Shubhodip Mojumdar. Okay.